Let's try to solve this question here. So the figure below shows the positions of 3-point charges Q1, Q2, and Q3. And Q1, Q2, Q3 are placed on the vertices of a right angle triangle. So in the diagram here, it shows that you have a right angle triangle with 90° over here. And they place Q1, Q2, Q3 on the vertices or the corners of the right angle triangle. Now they tell you that the resultant force acting on Q2 is F. So resultant force, it's the net force acting on Q2. So this net force here must be a combination of force exerted by Q1 on Q2 together with the force exerted by Q3 on Q2. If you combine these two forces using vector sum, you find that the resultant force is acting in this direction, which makes an angle of 45° with the vertical. So this is the vertical line, and the angle from the vertical to the resultant force is 45°. And now they ask you to find the charge of Q3. Okay, so let's try to think about the problem deeper. Okay, so over here, right, they provide you the charge for Q1 and Q2, but they don't provide you the electric charge for Q3. They tell you that the resultant force is acting in this direction, which is 45°. Okay, 45°, right, it's a very unique angle. It's not some very arbitrary angle. 45°, it's unique because if you form any triangle, if you form a triangle and you tell people that this is 45°, if you know this is 45°, you know that the other side should be 45° as well, and this will be a square. Okay, so if that's the case, right, then you know that the length over here should be equals to the length over here. A will be equals to B. Okay, so in that case, right, what they are trying to tell is if your resultant force is acting at 45° with the vertical, sorry, 45° to with the vertical, then it means that if you resolve it, right, the x component of the resultant force and the y component of the resultant force should be equals to each other. Okay, I'm talking about the absolute value, so I'm not caring about the sign over here. Okay, so knowing that will be very important because it will allow us to determine the force exerted by Q3 and Q2. Then from there, we are able to determine Q3. Okay, so here's how we are going to do it. We are going to prove that we are going to draw a diagram to show all the forces being exerted on Q2 first. And once we know all the forces that are being exerted on Q2, then we figure out what's our next step. Okay, we know that Q2 here will experience a few forces due to the presence of Q1 and Q3. So Q1 will exert a force on Q2. Since they're opposite charge, they should attract each other. They know that the force exerted by Q1 on Q2 will be pointing towards this direction. They want to attract each other, right? So it'll be pointing in this direction. So this is F21 by F12, sorry. It's exerted by charge 1 on charge 2. Okay. On the other hand, there will be a force exerted by Q3 on Q2. We don't know what is the charge of Q3, so we don't know whether Q2 and Q3 it's oppositely charged or they have like charges. If they're like charges, they should repel each other. If they're opposite in charge, they should attract each other. We don't know Q3, so we are unable to determine whether it's a repulsion or an attraction. But if you look at the question over here, they already tell you that the resultant force will be pointing in the third quadrant. You know that there are only two forces acting on Q2. One is F12, one is F by 3 on 2, F32. There's only two forces acting on Q2 over here. And you need to know that if you add up these two forces, right, the resultant force will be pointing in the third quadrant. So if you have one of the direction of the forces and you know the final direction of the forces, you should know that the second force should be pointing downward. Okay, you should know that the second force should be pointing downward. Okay, there's only two options. If Q3 and Q2 are like charges, then they will repel each other. Then the force experienced by Q2 will be pointing in this direction. This will be F32. This is if they are like charges. Then they will push away from each other, right? But if they are opposite charges, then they will be pointing in this direction. But from our deduction just now, we know that the resultant force is pointing at the quadrant. Therefore, we know that it's impossible that the second force is pointing upwards. Because if the force exerted by 3 on 2 is pointing upwards, then the resultant force will be pointing in the second quadrant already. That's impossible because they already tell us that the resultant force is pointing in the third quadrant. Therefore, we know that this must be the force exerted by Q3 and Q2. And from there, we can infer that the charge of Q2 and Q3 are opposite in charges. So if Q2 is a negative charge, we know that Q3 must be a positive charge. Okay, so I remove the one pointing upwards because that is not the correct force. The force should be pointing downwards. Okay, now we also know that Fx and Fy should have the same magnitude. So you know that the magnitude of F12 and the magnitude of F32 should be the same, or else you cannot get 45 degree. If F32 is larger than F12, then angle will be smaller. Then it'll be more pointing towards the downward. Okay. If F12 is greater than F32, then angle will be more inclined to the horizontal. But if it's 45 degree, that means that the horizontal and the vertical are exactly the same magnitude. So F12 and F32 should have the same magnitude. So from there, I can write that F12 should be equals to F32. Okay, again, if I don't put the arrow on top of the force, then that means this is a magnitude of force. So magnitude of force must be positive so they can equal to each other. If I write F12 is equals to F32, then I write arrow on top, then this is wrong. Okay, because they are not pointing in the same direction. Okay, it's important that I don't put the arrow on top because they have different direction. They only have the same magnitude. Okay, so knowing that, we can break open the force exerted by 1 on 2. We know that this is a force exerted between 2 point charges, so we can use K QQ over R squared. So this one is K, and the force is between Q1 and Q2. R squared is the distance between R12 squared. For F32, we know that it's between Q3 and Q2. Then this one is R32 squared. Okay, so there are some stuff that we can cross out over here. We can cross out the K, we can cross out Q2. So now we end up with Q1 over R12 squared and Q3 over R32 squared. So now you can do substitution straight away, or you want to rearrange your equation, both are fine. For me, I'll do my substitution straight away. So there's a modulus there, so I don't need to care about the sign. I'll just write the charge without caring about the sign. Okay, 40 nanocoulomb. R12 it's 0.040 meter square. Okay, Q3 we don't know, so we leave it as the absolute value of Q3 divided by R32, which is 0.080 square. So if we perform our calculation, I believe you get the absolute value of Q3 to be equals to 160 times 10 to the power of -9 Coulomb, or you can call it as 160 nanocoulomb. If you think that that's the end of the question, well, that's not it. There's still something that you need to finish it up. what you get over here is just the absolute value of Q3. You still haven't determined whether it's positive 160 nanocoulomb or negative 160 nanocoulomb over here. So what you need to do now is to determine whether it's a positive charge or a negative charge. But based on the discussion that we have just now, we know that because this force is an attractive force, it must be opposite charges, right? So let's try to write something to justify what is the sign of the charge, whether it's a positive charge or a negative charge. So we say, since the force exerted by 3 on 2 is pointing directly toward Q3, we know Q2 and Q3 must be opposite in electric charge. Okay, why point directly towards Q3 means by they must be opposite in electric charge. Okay, because if it's like charges, the force will point away from each other. But if it's opposite charge, the force will point towards each other. Okay, because attractive force, the force will point towards each other. If it's a repulsion force, then it will point directly away from each other. Now it's toward each other, therefore we know that it's an attractive force. Because we know it's an attractive force, we know that Q2 and Q3 must be opposite in electric charges. And now, since Q2 is positive, then you know that Q3, since Q2 is negative, sorry. Since Q2 is a negative charge, then Q3 must be positive. Therefore, you end up your answer by saying that Q3 is equals to positive 160 nanocoulomb. And that's how you finish up this question over here. Okay, the first step over here in which you calculate the Q3 over here is just the absolute value. There's no indication of whether this is a positive charge or a negative charge. To know whether it's a positive charge or negative charge, you have to look at the direction of the forces over here to deduce whether they are like charges or opposite charges. And from there only you determine whether it's a positive charge or a negative charge. So this is how you solve this question over here.